whenever you're looking at this. Welcome to our first lecture in the new normal, our cyber deal. All right, so I'm recording myself here, and I intend to put this onto the PowerPoint, and the PowerPoint will then be posted on a YouTube video. Yeah, so we have a YouTube channel now. I'm a YouTube star. Yay for me. All right, so the reason I'm doing that is because I've tried recording through Zoom, and I've tried recording through the PowerPoint itself, and while I can get them recorded, it will never, for whatever reason, pick up the videos. And so videos have been a very important part of my presentations, and so therefore I have researched, I've worked with my sons, and they have taught me how to do it this way. All right, so if you, I guess I'll email you and let you know if there's a problem with YouTube with you. All right, but we are going to be starting this for next Tuesday. So this class will be on the Tuesday class, which is, I'm looking up that date, so the 31st, yeah, 31st. So you can watch it before then, you can watch it on that day, you can watch it at that time if you like. I will try to kind of stay within our time period. I usually don't have any trouble with physical science doing that. The bigger problem, of course, is going to be labs. Today our lab is not too serious. I could take pictures, and I'll show you those pictures at the end of our presentation. You can do something like it at home as well, or draw things or something like this. We will have some labs in the future, though, that'll be very difficult to do. I will try to videotape them. I have videotaped some labs for marine biology, and it seemed to work okay, so I've got to figure that out. We're going to do a lab pretty soon on light, and it's such a fun lab, and I hope we get together for that. I really do feel like we will have time back in a classroom together. I'm not positive, of course, but I feel very optimistic about the fact that we will be able to do that. And so I'll save some of those more fun labs for that if we need to. All right. We will be going through the PowerPoint just like we do every week during class time, so I expect you to have your lab book out, and you'll be writing down your notes in there. We were supposed to have a quiz today, and I'm not sure how we're going to do that exactly. I think Google Classroom is going to be helpful on that, although I haven't figured it out yet. So I have to figure that out. Maybe by Tuesday I will have done that and get you that quiz. I believe you can actually take the quiz online, and then I can grade it online. So if we can figure that out, that would be great. If we cannot, or if I cannot, really, maybe y'all can help me. I can email the quiz, and then perhaps y'all could take a snapshot of it and get that back to me, or I could send the key home for your parents to grade it, or something like that. But go ahead and, do your study guide, and then I'll still give you credit for that. And then we'll just see how it goes. And then on those times when we do have labs that require a little more, I'll try to get those filmed for you and put them in. Okay, everybody. Well, so keep watching, and you're going to see the lecture take place right after this video. Thanks. I hope everybody's well out there. I'm okay, doing great, so hope y'all are well too.
All right, so here we go. This is our new schedule. I think I sent this out to you. You can see that we're right here on 13A, so we're starting a new unit. We're still talking about those 4 fundamental forces, and we'll be looking at that with the periodic table today. All right, and then we'll move into radioactivity, and then 14 and 15. So 15 down here is where we do the really fun light experiments. There is some pretty fun stuff with sound as well. So, wow, I hope we get together by here. Is that too optimistic? Not really sure. And notice we have our quizzes over here. And there is a final exam still. I know. We're still going to have that. It's going to be a sit-down exam, with the multiple choice, that kind of thing, similar to the midterm. All right, so you'll still need to be prepared for that. The final exam, by the way, covers the modules just from January through May. It's not totally comprehensive. All right. I think if we end up having some sort of Zoom classroom or something, we would have time for asking questions. Also, you're always free to send me an email to ask questions about anything that we're working on here. Okay, so let's get started. We're still looking at those forces of creation. Remember, there are 4 fundamental forces of creation, and I bet you can remember all 4 of them. Today we're talking about the one called the strong force. So in order to understand the strong force, we have to understand a little bit more about atoms and chemistry. All right, so we're looking here at atomic chemistry. Chemistry is all about atoms and how they interact with one another. So we'll be looking at the parts of the atom here. So in your book, you're going to see a place at the top of your book to write down the 3 most important parts of the structure of the atom. So we'll be seeing that we have protons. So go ahead and write down protons and put that positive charge there. You can even write positive charge if you like. In here, you'll see on our picture right here, the little red ones with the positive sign in them. Those are representing the protons. So protons have a positive charge. Electrons have a negative charge. The electrons, we have discovered, we're pretty sure, are actually spinning around the middle, which we call the nucleus, which holds the protons. Also inside the middle and the nucleus there, we have things called neutrons. Now, neutrons were the last thing to be discovered, so for the longest time, scientists didn't know anything about those. And so we'll see in a little bit, they don't have any charge. That's why they're called a neutron. They're neutral in charge. They don't confer any kind of charge onto the atom. Now, if you look at the picture over here, you can see there are 4 positive red circles in the middle, so those represent 4 protons. And we don't really care about the blue things right now. Remember, they don't have any charge. Those are the neutrons. But look at the electrons. How many of those are there? 1, 2, 3, 4. You see that? So it turns out when we're looking at an atom, it always has the same number of protons as it does electrons. That is not true about the neutrons, and we'll get to that. In fact, notice in this picture, what are there? 1, 2, 3, 4, 5. And so we will get to the reason for that here pretty soon. But for now, you need to know about those 3 words: protons, electrons, and neutrons. So what is inside an atom? The largest of these 3 particles is called the neutron, and the smallest is the electron. You can see kind of a comparative picture right here. The nucleus contains the protons and the neutrons, and the electrons orbit around the nucleus. Sort of how the moon orbits around the Earth, we have electrons orbiting around the nucleus right there. Notice how the neutron and the proton are similarly sized. Neutron's a little bit larger, but also notice, even why I say it's large, this is how much it weighs. 1.675 times 10 to the negative 27 kilograms. So that means that you put 27 zeros in front of that number. So it's 0.00027 times 1675. So you can see these are tiny, tiny particles, which reminds me that we've never seen these particles, and we never will. I am hopeful that when we get to heaven, God will have a strong enough microscope to show these to us, and we can see if we've been right all this time or if we've been wrong. That would be great, but we have no hope of actually on this side of heaven seeing these. If the proton and neutron are that small, check out the electron. It's negative 31. So we have 31 zeros in front of this number. In fact, it is such a small weight of the electron that when we are considering the weight of any atom, we ignore the electron. It confers no weight, no mass upon our atoms. All right, we call that a negligible mass. But the interesting thing about the electron is how influential it is on its charge. That negative charge is absolutely essential here. And interestingly also, the positive charge on the proton, which is so much bigger than the electron, is equal to the negative charge on the electron as far as charges go. So therefore, if we have a proton and an electron, we will end up canceling out any charge, and we will have an atom with no charge on it. All right, which is how we usually start when we're looking at certain atoms. All right, so here we go. This is sort of a little schematic about how the electron is just orbiting around the nucleus. So if you want to think of that nucleus as one proton and that electron as one electron, we have an atom of one proton and one electron, and soon we're going to find out. There's a chart we're going to look at. In fact, I'll have you open up your books, your textbooks, to pull out, I think it's on the front cover or the back cover, the copy of your periodic chart of the elements. An element that has one proton and one electron is always, always, always hydrogen. So we're looking at an hydrogen atom right now and how it must be, how it must look. Of course, we've never seen it. This is just our idea, our representation of it. All right, so how do we have any kind of concept at all about what atoms look like? Well, it has to do with these brilliant people who have gone before us and who have done experiments that would give us an idea of what atoms look like. And this guy right here is a man named Niels Bohr, and he was brilliant, a brilliant scientist. He actually came to live in America toward the end of his life, and he came up with a concept we call the Bohr model. I'm going to show you a picture of that here. This is the Bohr model, and that is simply that we have a proton in the middle, and we have electrons spinning in orbits. Now, it turns out that Niels Bohr is wrong, and that the Bohr model is probably not correct, but it is so useful, we still use it all the time. In fact, everything you'll be doing today as far as drawing and the model we'll make at the end is all going to be based on a Bohr model. So that's how useful it is. And you may wonder, well, if it's wrong, why do we study it? Well, it's only wrong in sort of a technical way, and that has to do with where are the electrons. So Niels Bohr felt like that the electrons were spinning in a fixed orbit. So this electron, for instance, is spinning around in this orbit, and it can't go anywhere else. Kind of like our moon doesn't really stray from its orbit, does it? But we've come up with a new concept. It's called quantum theory, and the quantum theory is that electron right there can be anywhere within here and here. It can sort of be anywhere. And of course, we're not sure that that's absolutely true either, because no science is absolute. Everything is still kind of in flux. We're always still discovering new things. But we'll be looking at the Bohr model a lot, and thanks to this guy, we'll look at a couple of other guys here in just a minute as well. In fact, here they are. All right, so when they first started wondering, when scientists first started wondering, what is matter made of? What is everything made of? They did some experiments. And the first thing we noticed was that that Mr. Thomson over here discovered that there were charges in it. All right, so he came up with the idea, what is known as the plum pudding model, and that is that we have this plum pudding, and within it there's positive charges and negative charges, and if there's an equal amount of positive and negative charge, it comes out with no charge at all. And so that's called the Thomson model, or the plum pudding model. And then one of his students was a man named Rutherford, and J.J. Rutherford came along, and he did a couple of more experiments, and his experiments kind of did away with Thomson's model. And the reason is that what he did was he bounced, he used gold. It happens he used gold, and he bounced neutrons in toward here. He bounced protons in toward the middle, and noticed that some of them would, he guessed that they would just go straight through. Okay, so they would just go straight through here because there'd be enough positive and negative that would change it. But what happened was he had some that bounced off backwards, some that did go straight through, and so he wondered, what about those ones that bounced backwards? Well, it may have come near this positive charge, and since positive charges repel, we know that it would have bounced backwards. And so it was Rutherford who came up with the idea that the positive charges must be concentrated in the middle of the atom, and the negative charges would be spinning outside of the nucleus somewhere. So he came up with the idea of what we call the planetary model, like orbiting with the moon type of a thing. The planetary model of the atom, also known as the Rutherford model. Well, Bohr built on Rutherford's work, and he came up with a similar, he agreed that Rutherford was right about that we have protons in the middle and electrons outside. And he was the one that came up with the idea of fixed orbits. All right, and like I said, it's been an important aspect of understanding chemistry. Well, then along came quantum theory. We have a guy named Max Planck, and then these men, Heisenberg and Schrodinger, came up with this idea of the quantum model. And it's kind of hard to see here, but we believe that there are still orbits with which these electrons travel, but the orbits aren't necessarily fixed. Like I said before, they can travel within that orbit area, but they're also not necessarily spherical or circular. So some of them, you can see right here, they actually have a figure 8 look to them. And so this is on a XYZ plane. It's hard to see here in 2 dimensions, but we have one going up, one going out, and then one coming straight out at you, okay, like a XYZ. And at any given time, there are 2 electrons spinning around in those little balloons out there. And of course, the larger the atom gets, the more electrons are going to be there, the more protons are going to be there. We're going to see more and more of these orbitals. All right, so let's take a look at a couple of them. Here's hydrogen over here. It has 1 proton, 1 electron. 1 proton means hydrogen. So the next one up, we're going to add 2 together here. We have 2 protons, 2 electrons. That's helium. Notice it also has 2 neutrons. All right. Then lithium. We have 3 protons, 3 electrons. That is lithium. So if you're looking at something, or if we give you an example and it says this atom has 3 protons, right away you know it's lithium. So where do you find that information? You find that information on the periodic chart of the elements inside the back cover or front cover of your book. It'll be the number 3 on there will be lithium, and 3 stands for how many protons are there. The reason we don't say how many protons and electrons are there is because sometimes those electrons, like this one for instance, might leave to go off and do chemistry somewhere, leaving lithium with only 2 electrons. We'll get to that. So here is what you're supposed to draw in your book. You're supposed to draw the model of helium. All right, so you see how we have 2 protons, we have 2 electrons, and there's the 2 neutrons in there. So what you want to do then is go ahead and draw that in your little box, put the plus and minus marks where they belong, and label them. Go ahead and say, proton, neutron, electron. You may want to take a little longer to draw this, so you can pause the video now to draw that, or you may have already finished. So I'm moving on. So these pictures are crazy. We are really still discovering what the quantum mechanical model looks like. These make sense because they have the spherical. Notice how those atoms can be anywhere. Electrons can be anywhere in that orbital right there. And then they get bigger, right? So some are in this orbital, some are in this orbital. And then things get kind of weird right here. This is supposed to be our little figure 8 area. So these are chemistry 1. All right, so in chemistry 1, you'll learn about the 1s, 2s, 2p, and even a little bit about 3s. But when they get really bizarre like these, that's for chemistry 2. All right, that gets very, very strange. And furthermore, it is all very theoretical at this point. And you may wonder, how in the world did we come up with these concepts? Well, when we do work with these, we can shine little, almost like x-rays on them and get shadows. And these shadows produce these kind of formations. So that's what's given us the idea that the orbitals might be shaped like this. Here is the famous periodic table of the elements. I would have handed one of these out for you at class to take a look at, and you will see that inside your book. I believe there's a copy inside this this module, in the chapter, but I also believe it's inside the cover of the front or back cover. And so let's take a look at it here. You'll notice a few things. There's colors on it, right? And so the colors mean something. And the colors are usually told to us right up here. There's some sort of key that tells you that. Some element charts have more information than others. But the big things I want you to notice is, let's take a look at hydrogen. We'll notice it has a number right there. The number is 1. That is its atomic number. It's got a symbol. It's H. That's its atomic symbol. It stands for hydrogen. Sometimes our atomic names will make sense. H for hydrogen makes total sense, but let's look at iron right here. Fe, how in the world does that mean iron? Well, it turns out the Latin, Greek, or whatever word for iron is ferric, and so they got it from there. Can you tell me how many protons iron has? Take a look at that. Yeah, y'all got it? It's got 26 protons. How many electrons does it have? You should have guessed 26. There we go. Over here to helium, which you just drew, check it out. Its atomic number is 2. Its atomic symbol is He. Notice that almost all of our elements are either one letter or two letters. The first letter is capitalized. The second letter is lowercase. That is a general rule we follow. For these weirdos down here, you can see the 3 letters. Mostly that has to do with these haven't really been named yet. Okay, so they're new. They have been synthesized in a laboratory. You know, why do scientists synthesize elements in a laboratory? Because they can. All right, and it's very expensive, but they get to make a name. Literally, they can name it after themselves. So some of these in here you can see may have some names that look like they were named after somebody. Yeah, I know francium was named after the country of France, right there. Yeah, but there are some in here with people's names associated with them. All right, so we will refer back to this chart several times. I'm sorry I can't have it up the whole time while I'm talking, but you can have it in front of you in your book. Oh, really quickly, the groups here down this way, they're grouped this way because this one, hydrogen, lithium, sodium, potassium, with a K, weird, and the rest of these down here, they all tend to act similarly chemistry-wise. So when we're doing chemistry with those in group 1, they act similarly. And because of that, they show something known as periodicity, and that's where we get the word periodic. Also, group 2, they act similarly to each other all the way over here. This group at the end with helium, neon, argon, krypton, xenon, radon, these are very special over here because these are called the noble gases or the inert gases. And what that means is that they have the exact number of electrons in their orbitals that fill it up. So they get filled. And because they're filled, we can think of it as this way, they are fulfilled, all right? So they are happy. These are the happy atoms over here. They don't need any change at all. And so furthermore, they don't do any chemistry. All right, it's very hard to make these perform in chemical reactions because they don't have any electrons to trade, give away, steal away, accept, anything like that. They have their electron shell filled out there, so they don't tend to do much. I will say that we know things about them. For instance, with neon, if we shine electricity through it, it will glow a certain color, and all of these will do that. So that's how we make neon lights. Most of the lights you see, for instance, the fluorescent lights that are in most buildings, even our classroom back at the church, they have a gas in there which happens to glow a sort of whitish yellow color. I believe that's argon that does that. But I'll show you a picture in a minute of the different colors that glow when you shine electricity through them. You'll notice a lot of these on here. You've heard of them. Carbon's a big one. Oxygen, obviously, you've heard of. You've probably heard of nitrogen, phosphorus, sulfur, chlorine, aluminum. So a lot of these you've definitely heard of. I will say when they get past a certain number, we start to lose track because they're stranger and stranger. Furthermore, this group right here, notice they've been just pulled right out. Where'd they come from? See, here's number 56, and then 57's down here. So why in the world does that one come all the way down here? Well, it turns out these guys do not follow any rules. They're the rule breakers. And because of that, we can't give them periodicity, right? Because they don't follow the rules. Whereas these guys right here in the middle do, although this big section of yellow stuff in the middle right here, they also tend to not follow the rules very well. And so they're kind of strange. That includes things like, cobalt, nickel, and iron and copper, some of the metals there, zinc. But these in groups 1 and 2, and in groups 13 through 18 here, which really we call 3, 4, 5, 6, 7, and 8, they are very easy to predict what they will do chemistry-wise. So we use those mostly in Chemistry 1. All right, we're going to watch a little video here.
The periodic table is instantly recognizable, It's not just in every chemistry lab worldwide. It's found on t-shirts, coffee mugs, and shower curtains. But the periodic table isn't just another trendy icon. It's a massive slab of human genius, up there with the Taj Mahal, the Mona Lisa, and the ice cream sandwich. And the table's creator, Dmitry Mendeleev, is a bona fide Science Hall of Famer. But why? What's so great about him and his table? Is it because he made a comprehensive list of the known elements? Nah, you don't earn a spot in Science Valhalla just for making a list. Besides, Mendeleev was far from the first person to do that. Is it because Mendeleev arranged elements with similar properties together? Not really. That had already been done too. So what was Mendeleev's genius? Let's look at one of the first versions of the periodic table from around 1870. Here we see elements designated by their two-letter symbols arranged in a table. Check out the entry at the third column, fifth row. There's a dash there. From that unassuming placeholder springs the raw brilliance of Mendeleev. That dash is science. By putting that dash there, Dmitry was making a bold statement. He said, and I'm paraphrasing here, y'all haven't discovered this element yet. In the meantime, I'm going to give it a name. It's one step away from aluminum, so we'll call it Eka-aluminum. Eka being Sanskrit for one. Nobody's found Eka-aluminum yet, so we don't know anything about it, right? Wrong. Based on where it's located, I can tell you all about it. First of all, an atom of Eka-aluminum has an atomic weight of 68, about 68 times heavier than a hydrogen atom. When Eka-aluminum is isolated, you'll see it's a solid metal at room temperature. It's shiny, it conducts heat really well, it can be flattened into a sheet, stretched into a wire, but its melting point is low, like freakishly low. Oh, and a cubic centimeter of it will weigh 6 grams. Mendeleev could predict all of these things simply from where the blank spot was and his understanding of how the elements surrounding it behaved. A few years after this prediction, a French guy named Paul-Émile Lecoq de Bois-Baudran discovered a new element in ore samples and named it gallium after Gaul, the historical name for France. Gallium is one step away from aluminum on the periodic table. It's Eka-aluminum. So were Mendeleev's predictions right? Gallium's atomic weight is 69.72. A cubic centimeter of it weighs 5.9 grams. It's a solid metal at room temperature, but it melts at a paltry 30 degrees Celsius, 85 degrees Fahrenheit. It melts in your mouth and in your hand. Not only did Mendeleev completely nail gallium, he predicted other elements that were unknown at the time. Scandium, germanium, rhenium. The element he called Eka-manganese is now called technetium. Technetium is so rare it couldn't be isolated until it was synthesized in a cyclotron in 1937, almost 70 years after Dmitry predicted its existence, 30 years after he died. Dmitry died without a Nobel Prize in 1907, but he wound up receiving a much more exclusive honor. In 1955, scientists at UC Berkeley successfully created 17 atoms of a previously undiscovered element. This element filled an empty spot in the periodic table at number 101 and was officially named Mendelevium in 1963. There have been well over 800 Nobel Prize winners, but only 15 scientists have an element named after them. So the next time you stare at a periodic table, whether it's on the wall of a university classroom or on a $5 coffee mug, Dmitry Mendeleev, the architect of the periodic table, will be staring back.
All right, there we go. So that kind of explains the founding of that chart that is so important to all chemists everywhere and to all of us, really. So we'll be looking now, the arrangement in that chart is arranged by element. So we need to get a good working definition of what is an element. So here you go. An element is a collection of atoms that all have the same number of protons. It's all about the protons. All right, we don't really change protons. We can change electrons by doing chemistry. We can share electrons, we can give them away, we can do all that. But with protons, to mess with protons takes a lot of energy, very expensive. That's called nuclear physics. All right, so we don't mess with protons. Protons are the identifier of an element. All right. The atomic number, we discussed that. It is that number that tells the number of protons in the atom. So hydrogen has 1, so its atomic number is 1. Helium has 2 protons, so its atomic number is 2. The mass number, however, is the number of protons and the neutrons in the nucleus of the atom, because neutrons, while they don't give any charge to the atom, they do give mass to the atom. All right, so the mass number is typically found underneath the symbol or somewhere in that little box. If you have a very, very simple periodic chart of the elements, it'll give you the symbol, the number, and the mass. If you have a fancy one, like we get in college, it'll have a bunch of other things in there too, melting points and various things like that. Remember, you can pause this slide if you want to take more time to write these things down. Okay, so here it is. We have helium. There's our atomic symbol, He. There's our atomic number, 2. So how many protons does helium have? 2. That's correct. Now, check out that atomic mass down there. What is that mass? Look at that. How nice and neat. 4.00. Very neat. So if I know that I have 2 protons and my atomic mass is 4, and neutrons are the only other thing that can give weight or mass to my atom, then what does that 4 tell us about how many neutrons there are? So all we have to do is a little math. So we take that number 4, we subtract out what we know to be the protons, which is 2, and we get the number 2. So what can you tell me about the amount of neutrons in helium? There are 2 of them. Do you get it? So we will see, this was a very simple one. We will see some more complex ones. Some of them, as they get bigger and bigger, they might just load a bunch of neutrons into there. That, you know, God created them for that, I'm not sure what reason, but he created them on purpose that way. And we'll see next time when we talk about some of the other forces, how sometimes when they have a lot of neutrons, they tend to be unstable and they start to fall apart all by themselves, and that's called radioactivity. All right, so take a look here. We have hydrogen and helium. This is showing our Bohr model. So we know how many protons are in hydrogen. We know it's 1 with 1 electron. With helium, we know there are 2 and with 2 electrons right there. All right. Ah, looky there. That's something we know about helium, right? Helium is lighter than air, and helium is an element. Okay, if it's an element, then it cannot be manufactured. So if you've had helium balloons at your party ever, then you had to get that helium from somewhere, and that helium had to be mined. It can't be made. So there's not like a helium factory out there which is producing helium. The only way we can get helium is by mining it. Now, it's under the ground. It's stuck in pockets somewhere. I'm not exactly sure how we mine it because it's so lightweight that it just would, you know, float up as soon as we tapped into it. I will tell you an interesting story is that the vast majority of helium, which is found naturally, right, is found in the United States of America. Not sure why, but we therefore have kind of a corner on the market of helium, and everybody gets their helium from us. Now, once the helium is all gone, it's all gone. Yeah, we're not making any more helium. Technically, you could make it, you know, in a lab. I mean, technically, it would be very, very expensive, and possibly, yeah. I don't know that it's possible, but not very practical in any way. All right, so you know that helium has 2 protons and 2 electrons, and it floats when it's in a balloon. So what do you think about hydrogen? It turns out hydrogen only has 1 proton and 1 electron. Do you think it floats as well? It turns out it does. But I want you to remember something very important about where these 2 are on the chart. So if you're looking at your chart, take a look at it. Hydrogen's all the way over to the left in that top little box over there in group 1. And helium all the way over to the right in that special grouping. Remember that grouping? That's the group that doesn't do any chemistry. All right, so helium is very unreactive. So there's a great story in the 1930s. The German government wanted to buy helium from America because they had these famous airships, these Zeppelins they called them. And the Zeppelins were these giant, we call them blimps, you know, and they're up in the sky and they can go a long way. Well, they thought at the time that the Zeppelin was going to be the luxury travel of the future, that the rich people would get on these Zeppelins and fly overseas, kind of like how some people would get on giant cruise ships or something today. And so at the time when the Germans asked to purchase a bunch of helium from us, we refused to sell it to them, and that's because there was a new political party in Germany at the time known as the Nazis. And so we did not want to sell anything to the Nazis or in any way support them. And so we told them, no, we will not sell you any helium. And they said, fine, no problem. We don't need your helium. We will just use hydrogen. All right, so is there a problem there? Does hydrogen float? You better believe it floats. It floats even a little better than helium. Okay, so will it float one of these giant airships? Yeah, it sure will. There's only one problem, and it has to do with the periodic chart of the elements, and that is that hydrogen is very, very chemically reactive, whereas helium is not. So take a look. This is a famous air disaster known as the Hindenburg. It happened, it was actually in America, it was in New Jersey. This is going to loop through, you're going to see it again. So picture that airship right there, filled with hydrogen, and there was some sort of spark. We're not exactly sure what caused it, even to this day, but look what happened to the Hindenburg. Yes, that's because hydrogen is much more reactive than helium. Had there been a spark when there was helium in there, would this happen? No, not at all. There could have been a fire, but it would have been a small localized fire. This turned into, obviously, a giant disaster. There were people killed on this, but interestingly, a lot of people actually survived by jumping out. Some of them had broken bones and things, but they did survive. So anyway, chemistry is important. So here are noble gases. Helium right here, which is the one that floats so nicely. When you shine electricity through it, it glows kind of this. What color would you call that? I don't know if that's purplish. These colors don't look very similar. Neon is red for sure. I was wrong about argon. Look, it's purple. It must be krypton in our lights in the fluorescent bulbs right there, because it's glowing kind of a white yellow. And then xenon right here is going to glow kind of what do you call that? A purplish blue. Yeah, so remember, they're not reacting at all. What they're doing is just when electricity is passed through them, it excites them. And it excites their electrons, and the electrons start to quiver back and forth and move faster and causing this glow. Sometimes they'll hop between of the orbitals, and when they drop back down from the orbital, that's when they'll send off a glow. It's sort of the energy being released. But you have to have electricity shining through them to do that. It's not changing them. Whereas chemistry will change not the atoms, but change the molecules that might be in there. Someday when you take chemistry, you'll learn all about how molecules are switch and swap electrons, and that's what chemistry is. All right, so let's come up to the isotopes. Your book does talk very clearly about what isotopes are. So right over here to the right on our screen, we see a atom of carbon. All right, I'm telling you that carbon has 6 protons. They're the blue ones. 1, 2, 3, 4, 5, 6. And 6 electrons. 1, 2, 3, 4, 5, 6. How many neutrons in this one? Neutrons. The red ones, 1, 2, 3, 4, 5, 6. Okay, how nice. So we have 6 protons, 6 neutrons, and 6 electrons. This is carbon. But sometimes things can change. And what can happen is that we can actually have more neutrons. Now, we can't have more protons. If we had more protons, would it continue to be carbon? No. 6 protons is carbon. 7 protons is something else. It's nitrogen, I think, right? All right, so an isotope, here you go, you're going to write this down. An isotope is 2 or more atoms that have the same number of protons, of course, but a different number of neutrons. Notice I didn't say anything about electrons here. We're talking about protons and neutrons. So isotopes are elements that have differences in their nuclei. Okay, the nucleus is different. We're looking at our example of carbon. So it has an atomic number of 6. So therefore, we know it has 6 protons. Its atomic mass is 12. So therefore, what do we know? It has 6 neutrons. Okay, so 6 protons and 6 neutrons in the nucleus makes carbon-12. But carbon-13 has 6 protons and 7 neutrons. You see 6 plus 7 is 13, right? And then we have even one more, carbon-14 has 6 protons and 8 neutrons. You may have heard of carbon-14. We will talk about it again, I believe, either next week or the next. And that's because with those 8 neutrons in there, it is unstable. It's unstable and falls apart all by itself. Remember, that is called radioactivity, and we'll learn about that next time, or one of the next weeks. So here, let's take a look at those carbon isotopes right here. The vast majority of carbon is this one right here, carbon-12. I mean, something like 95% of all carbon is this. And then we have the next group is carbon-13. Notice we have 7 neutrons. If you want to count them or try to count them, you can. And then carbon-14, a very small number of carbon, small percentage-wise, is carbon-14. And notice it does say that it's radioactive. It's unstable. It falls apart. Here's some isotopes of oxygen. We have oxygen's atomic number is 8. And so we know there are 8 protons and 8 electrons. You counting those? And an isotope would be with 10 instead of 8 neutrons. And notice it's called oxygen 16 or oxygen 18. But they're both isotopes. Even though the vast majority of oxygen looks like this, both of them are the isotopes of oxygen. Just one is more prevalent than the other. So here we have nitrogen. Notice its atomic number, 7. What does that tell us? That tells us the number of protons. Check out this. That's its atomic weight or atomic mass, 14. So that tells us the vast majority of the time, nitrogen has how many neutrons? It has 7. So you can see, check this out though, look, 0.007. So 0.007 amount of the time, nitrogen will have 8 neutrons. We were going to draw that right over here on the board. I was going to draw that for you. I'm not sure if you're supposed to draw that. You might want to draw that. Also on that previous one of the carbons or the oxygens, if you want to pause the screen and go back and draw those in your box, you certainly can. All right, we have an example problem that you have in your book. Example 13.1 on page 319. This is similar to maybe a quiz question that you might have. And so let's check it out. All atoms that make up the element nitrogen have 7 protons. If a particular nitrogen atom has 8 neutrons, what is its name? And how many electrons does it have? All right. It's called nitrogen 15, okay, because 7 plus 8. It has 7 electrons. See, that was kind of a trick right there. How many electrons? Well, that didn't change anything, right? It didn't change anything. And here they are. So there's nitrogen 14, and then we have nitrogen 15. And the only difference is nitrogen 15 has an extra neutron in it. Okay, continued. Which of the following atoms is an isotope of nitrogen 15? What is its name? Okay, so do you remember what the atomic number of nitrogen is? Look at your chart. It was just on that last slide too. Let's see. 5 protons, 5 electrons, and 10 neutrons. Could that be an isotope of nitrogen? What about 8 protons, 8 electrons, 7 neutrons? What about 8 protons, 8 electrons, 8 neutrons? Or 7 protons, 7 electrons, 7 neutrons? Now think about it. You got to take a look at that atomic number. There's only one of these that would be considered nitrogen. You got it? Only D is correct. That's because 7 protons means nitrogen. It doesn't matter anything else. 7 protons means nitrogen. So that can't be nitrogen. Neither can that or that. Okay, so just remember that that chart of the elements tells you lots of important information. Okay, this is something that's also in your book right here. We have our orbitals. So the Bohr orbit, he decided that electrons were traveling in different orbitals. They weren't just all nilly-willy, traveling around. So we're going to be looking at the 5 different ones here. So these are actually called the S1, S2, and then P1, P2, S3. It's chemistry. You don't have to worry about why they're called that. It has to do with the amount of energy that is in that orbital over there. So the first orbital can only hold 2 electrons. That's it. So if you think about your helium that you drew right there, it has the 2 electrons. So remember, helium was full. Yes. So check it out down here. 8 electrons now. I mean, this is electrons in the outer area there. All right. So, and on our chart of the elements, if you see our next noble gas is number 10, which is 8 plus 2. but 8 in the outer shell or the outer orbit, which means that it's full, and that is neon, meaning that neon is also like helium. It is full and doesn't do any chemistry, right? And then we move on to the bigger and bigger ones as we go down the periodic chart. It gets rather cumbersome there. So what are the orbitals? That's just the spot where they locate there. So notice, this is a picture of a carbon atom. Notice only two can be in that first orbital. And then the second orbital can actually hold 8, but how many is it holding? Only 4, because we know carbon's number is 6. So we have 1, 2, 3, 4, 5, 6. So now we're looking at those electrons, right? Because the orbitals are for the electrons. The protons and neutrons are in the nucleus. The electrons are orbiting. Okay, so orbitals are where electrons go. And this kind of shows what I told you earlier. We have 2, then 8, then 18, and is that number right there? And it's talking about energy levels. So for instance, when helium was glowing, these 2 electrons probably jumped out a little bit and then fell back down to level 2, which caused them to glow. All right, so these are just energy levels of where the electrons are and how they will go through with chemistry then. So you can see right here. Notice in group 1A we have hydrogen, lithium, and sodium. Now lithium is much bigger than hydrogen. It's got 3 protons. Look, sodium has 11 protons. But notice what they have in common. This outer electron is there's just one of them. Remember how I told you these tended to act similarly? Well, that's because they all have the same number of electrons in the outer shell. Okay, that's called a valence electron. Also not important for you right now, but it's the valence electron. So notice over here, helium's got 2, it's full. What does neon have? 1, 2, 3, 4, 5, 6, 7, 8, it's full. Don't forget to count those 2, making 10. Argon, look, it's full. Its outer orbit is full. But notice, for instance, on fluorine and chlorine, they have 1, 2, 3, 4, 5, 6, 7, and they would like to have 8. All right, that's where chemistry happens. Right down here, chlorine would like to have 8. So think about this. Sodium has 1 extra and would like to actually give it away so it'll end up looking like neon. If it gives it away to chlorine, chlorine will take it and end up looking like argon. So the goal of every atom out there is to look like the guys in this last row right here, okay? Is to put on a cloak of some sort, electrons, and look like these guys over here, at least from the outside. They can never look like them from the inside because they won't change the number of protons. But by changing the number of electrons through chemistry, they can actually, from the outside, look like the nobles over here. They look like a king. So that brings us to our strong nuclear force. That's the subject of our lecture today, right? We're finally there. So remember that protons have a positive charge. But we know that like charges repel. That's one of those fundamental truths, right? That like charges repel each other. So the plus should repel each other. How is it that they don't repel each other in the nucleus? Think about some of those really large nuclei with, 50 protons in there. How are they not just bursting and, popping open? That's because of the strong nuclear force. Y'all, it is a miracle. It's a miracle. It's a force that's so strong that it overcomes that natural repulsion. If you take 2 magnets that are, the same charges and put them next to each other and hold them really with your strength, you can keep them together, right? Well, that's how God is keeping every atom together, with his strength pulling those through this strong force. Now you know why it's called the strong force. In fact, it's the strongest force in the universe. Isn't that crazy? If it weren't there, y'all, nothing would hold together. It would be, everything would just be falling apart all the time. So I just find it fascinating, absolutely fascinating. So the strong nuclear force is the strongest force because it overcomes the natural repulsion of like charges in the nucleus of the atom. This might be what you want to write down for your definition. So you can pause it here. Let's watch a little video about it.
If you're interested in learning about particle physics, one of the key topics you need to understand are the forces that come into play. For instance, we know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. Of these 4, we have at least a little familiarity with gravity and electromagnetism, so naturally, I want to tell you something about the strong nuclear force. The first question you might want to know the answer to is, how do we know that there's a strong nuclear force at all? Well, this is something we've known for essentially a century. In 1911, Ernest Rutherford discovered the basic structure of the atom, which is that it consists of a small and dense core of positive electric charge called the nucleus, surrounded by a cloud of negatively charged electrons. And in 1917, he discovered the proton, which meant that the nucleus consisted not of a big blob of electric charge, but of a whole bunch of smaller blobs held together. Remember that each proton can be imagined as a tiny ball with a positive electrical charge. They say that opposites attract, and that might well work for couples, but it's definitely true for electrically charged particles. On the other hand, like charges repel each other. So let's imagine a simple nucleus consisting of just 2 protons. Since each proton has a positive electrical charge, they push each other apart. And they don't push each other apart a little bit. The repulsion force is about 20 pounds. 20 pounds is a respectable force in the world of you and me. In the particle world, it's huge. It's so big that if you let the 2 protons go, they'd push until they were moving away from one another at a speed of over 8,000 miles per second. And I just picked the simple case of 2 protons. In the case of uranium, there are 92 protons all packed together in a ridiculously tiny volume, and a proton on the surface is repelled with a force of just over 70 pounds. So, if these protons are all getting pushed apart from one another, what keeps them together? There's only one possibility. There has to be a force that is even stronger that counteracts the electromagnetic repulsion. And the name for that force is, you got it, the strong force. What do we know about the strong force? Well, we know that it's strong, and it can't just be a little stronger than the electromagnetic force. That's because if the 2 forces were pretty similar, it would be easy to knock protons out of the nucleus of atoms. And we know that's not true because nuclei last for millions and even billions of years. So the strong force has to be way stronger. From tests, we know that the strong force is about 100 times stronger than the electromagnetic force. But the story is a bit trickier than that. After all, if the force is so high, what keeps the strong force from continuing to gather protons until the whole universe consists of one big nucleus? If we look at the periodic table, we see that the highest stable element has no more than about 100 protons in it. And yes, I know that the nuclei also contains neutrons. That doesn't change much in what we're talking about here. So it seems that with more than about 100 protons, the strong force can't hold it all together. What's that all about? It turns out that there is a property of the strong force that is quite different than the electromagnetic force. Electromagnetism has an infinite range. In principle, 2 electrically charged particles will feel a force between them if they're separated by the entire universe. Okay, the force would be small, but in principle, it's true. In contrast, the strong force is more like a contact force. When 2 protons touch each other, they feel a strong force. Pull them apart a little bit, and the strong force goes to 0. In a way, the strong force is a little like Velcro. When 2 pieces of Velcro aren't touching, the 2 pieces feel no force toward one another. So that's the strong force. It is stronger than the electromagnetic force, but it has a much shorter range. And those 2 properties explain why low-mass nuclei are stable and heavy ones aren't. In the heavy ones, all the protons in the nucleus push against all the other protons, while the strong force only feels the force of its neighbors. And this is all pretty cool. What I've told you here is actually nuclear physics, not particle physics. I'll make another video that brings the strong force into the particle world. The strong force is a fascinating subject, and it is the strongest known force in the universe. Well, the second strongest force.
All right, that made total sense, right? Yeah, a lot of smart people out there figuring these things out. It is amazing. But here's another one of our smart guys. This is Hideki Yukawa, and he thought that perhaps that strong force had an element to it that involved little tiny particles. Okay, so he proposed that protons and neutrons exchange tiny short-lived particles called pions. Okay, so the pions would be, remember when we threw the ball back and forth to each other, right? And when we were close together, it was easy to catch. When we were farther apart, I think we were talking about gravitons, right? And we also mentioned that same thing when we talked about the packets of light, right? The photons. Well, so he believed even on a tiny, tiny, tiny scale, we're looking at something called pions. So it's still just a theory. He did get a Nobel Peace Prize for it. It says Nobel Peace Prize in Physics. It's a Nobel Prize in Physics. There's not peace at all. So that's a misprint right there. But in 1947, and so they showed that the theory was possible. Here's his idea, that we have a proton and a neutron in the nucleus, and they're tossing this little pion back and forth. And somehow that little thing right there will allow a communication and will also lend somehow to the strong force. Remember, the strong force is really between protons, but here our neutron is helping with that. It's the hydrogen that doesn't have a neutron in it typically, and so because it doesn't need it, right? It doesn't have to have any strength because it only has one proton in there, so it doesn't need anything. But when you get bigger with more protons, that's typically why we have more neutrons. And what this scientist was suggesting was because those neutrons help by throwing around these pions. There are other things in there too, quarks and gluons and strings and crazy stuff like that, all very theoretical at this time, but research being done to show that there is quite a lot of evidence to suggest that there are these tiny subatomic particles that are somehow helping with the strong force, with other nuclear forces, and with chemistry and this kind of thing. This is nuclear physics. Not chemistry anymore. So therefore, nuclear physics can get very, very complex and in often cases very theoretical. All right, so here's our chart of the elements again. I put this back up. I would have had this up on the screen for you as we did our lab. And so our lab is I was going to give you an assignment for an element. It would have been elements either 3 through 10 or so. So you could have picked lithium or beryllium, boron, carbon, nitrogen, oxygen, fluorine, or neon. And then I'll give you a plate, and you can do this at home. It's going to be a model, and we're going to use M&Ms to do this. Okay, so here's my picture that I did here. You can see in the middle, how I normally do this activity, y'all, is that you would have normal-sized M&Ms, and they would be in your nucleus. And you know those little mini M&Ms? You can make, those would be the electrons. Now, wouldn't you know it, when I went to the store, and waited in line and all that stuff to go my turn into HEB, there were no M&Ms left, y'all. That apparently is one of those essential items that we must have in the time of crisis. So all of the M&Ms were gone. So I happen to have these healthy M&Ms here, but I had peanut M&Ms and regular-sized M&Ms. So that's what we're showing here. My peanut M&Ms are the nucleus, so those are our protons. And then the green ones there are going to be our electrons. So let's count. So I would have, given you, and you would have had to make your model and show it to me on your plate like this. All right, so let's count here. We have 1, 2, 3, 4, 5, 6. So look at your chart of the elements. What atom have I made here with 6 protons? Notice I have 1, 2, 3, 4, 5, 6 electrons. I tried to show it where these 2 were in this first orbital and these 4 were in this second orbital. It's a little hard to see right there. Okay, have you got it? Yeah, it's carbon, right? It's carbon. And most carbons are carbon-12. And if it's carbon-12, that means their atomic mass is 12, which tells us what? Okay, my next picture. I've added in the neutrons. How many neutrons are there? 1, 2, 3, 4, 5, 6. There we go. So this is a model in M&Ms of carbon-12. All right, so y'all would have done that. We could have switched around and you could have made some of the other ones. Most of my students like to pick neon because it will have the maximum number of M&Ms in there. Afterwards, of course, you've been touching those M&Ms, you would have to eat them or throw them away. But yum, I ate mine. They were delicious. Mine are the healthy organic ones. So that was our lab today, y'all. Keep reading Module 13. And we're going to, that's it. So next week in 13B is when we're going to learn about radioactivity. All right. It's actually a lot of fun. We'll do, well, hopefully a fun experiment I can show you here, or who knows? You never know. We might be back together by then. All right. Okay, kiddos, I hope that you got through this okay. I hope you could hear everything and that it went well. Make sure to give me feedback. You can email me, whatever, to tell me how it went. Okay. Thanks a bunch. Have a great, great week.